Okay, so I have essentially decided that we're going to look at more shading features, but I'm going to try and keep it pretty generic so that since you guys don't really have, I don't know if you guys are using small louvers or if you're using kind of wall extension, high mass louvers that are built into the architecture or, kind of integrated overhangs. I'm going to try to keep that pretty generic so that you can break these elements down in any way you should need to if you're doing something that's somewhat, I guess, kind of grid based. On the east and west on the east and west facade, if you should have anything directed directly east or west, you're going to need something that's broken down across the facade, right? So either you're doing deep vertical louvers that have a wider space between them, or you're doing a lot of very thin and shallow ones, but you're doing them very frequently across the surface. So we're going to use the is this yeah so we're going to use the western side of our model for this one. And to start, I'm going to first grab, I'm just going to grab, well, let me grab it. Not the edge. Oh, all right. So I'm first just going to grab one of the surfaces here, and I'm going to copy it over to the other side. Okay, nothing too special. I don't have a specific depth or anything like that. I just copied it over. It is what it is for now. And for this exercise, I'm going to I'll start off with a subdivided grid, and I'll show you how to kind of create things off of a grid and isolate sets of geometry off of it, which is interesting, at least, kind of. So it's sort of like what we did here. We did a subdivide surface with a divide and reference the original surface. In fact, I could copy this down, or you guys could recreate it, but if you have it, you can just copy it down, but I'll recreate. So I'll reference in a surface with params and do the subdivision just like we've done so many times before. Divide domain squared with an isotrim subdivide surface. And then I go to surface, freeform, utility, isotrim. Okay, and I can set some sliders, 0 to 10. I think is kind of an alright place to start. And I'm going to keep the subdivisions kind of small. This looks like it should be okay for now. Get in perspective here. Oh, you can't even see that. Let me fix the lights and then I'll give you a moment to get caught up on this. Next step for me, at least, is that I'm going to turn off the glazing layer just to make it a little easier to see the red lines and subdivision lines. You good back there? Okay. And let's basically just start breaking it down, right? So I mentioned a while back, and I haven't really kind of reiterated this enough, that Grasshopper is a constant state of constructing geometry, deconstructing the geometry, and then reconstructing it into something else. The important thing that I think you should be aware of is that the geometry that you're breaking down is you have to be very careful about how you organize it, right? So I did this example before where I went to deconstruct under surface analysis. And I use the edges. Okay, so the edges were very, very important for me to isolate, and let me show you why. So if I wanted to create something like a whole entire waffle frame, right, I need to extrude it. Okay, and remember, extrusions usually use the surface normal. And I'm really trying to get you guys to understand surface normals all the time, because if you're not using surface normals, you're basically gonna, actually, maybe we should be doing a curved surface for this, so I can show you why. Do you guys have a firm understanding of why we use surface normals all the time yet? Because we're doing a lot of rectilinear stuff because your design class is. But all right, let's do this then. Rather than on this model for now, let's first explain why surface normals are so important. I think you'll get a lot more out of that. So in the front view, I'd like you to just create an arc. It doesn't have to be anything super special, but make it kind of compound and not exactly regular. A 4-point arc like that would be fine. And I'm going to copy it over like that and then mirror it somewhere so that in perspective it kind of looks like you've got one that kind of goes one way and the other one that kind of goes another way. It doesn't matter how regular or irregular it is, just don't make it the same. And then loft the two of them together. So your surface here is pretty irregular. It's not a singular curve. That's important. I want you to go back to the original surface that you created and reselect the surface that you just created right now. So I'm going to set one surface and go here. And let me assign it to a layer. I'll assign it to layer 5 and then turn layer 5 off. All right. Did you guys get there all right? Do I need to pause? Pause? Yeah. Okay. All right, resuming now. The point I'm trying to get at here is why are normals so important? If you look at the points or even the panels, right? The points and panels. Let's say you want to build something off of this surface. You have to use the surface normals, or else you get sort of an undesirable result. So if I want the points on the left side over here to move away from the surface perpendicular to the surface itself in that location, and I want the points over here to move away perpendicular to the surface here, I have to use a surface normal, because if I go to transform and I use move away from, yeah, that's good, and I use move, I can plug in, say, the vertices, and instead of moving away from that surface, it actually moves up. Now we have this other Euclidean feature right here that basically has the geometry to move, the geometry to move away from, and the distance. So essentially, if you wanted to move your vertices away from the original surface, you could do that. However, it's really chaotic. They're not really moving in a logical way. Let's wait, hold on, maybe that needs to be flattened. No, I guess not. So here's kind of the trick, or at least part of the trick. I'm going to show you visually with the faces instead, because points get more complicated. Rather than mapping the normal to the surface itself, I'm going to apply the normal to each of the faces and then move the faces along that direction. So if I go to surface analysis, and I set up that whole normal mapping sequence, remember we use evaluate surface, we use surface closest point. We plug the UVPs in, and we need the area to get the centroid. So I'll plug the faces into the area, which gives me a centroid, which I can use as my point, and then I plug the faces into each of the surfaces for the normals. Now notice how it creates a plane that is in line with each of the surfaces I just created, rather than just one normal. The reason this is important now is because I can amplify I'm going to say 0 to 10 along that normal and move the faces that vector distance, so, or along that vector. And so here's what it is. It turned off? Oh, it is turned off. Turn it back on. Oh, I need to be negative. I'm flipped here. Negative. You might not need to be negative, but so now what's happening is they're actually moving away from the surface in their respective directions. Making a little more sense now? So why is that important for us when we're mapping it to the surface over here? Anybody? Anybody? Hmm?
It's just directly in front of it. You're just trying to.
Well, I like to describe it as this. Oh, where'd it go? Here it is. I like to describe it as this. It is the easiest way for me to take a surface like this and construct, subdivisions on it, whatever it is, whatever assembly. And if I should need to change the position of my building or the orientation of that surface, it's already preloaded for me to just simply rotate it and the surfaces go with it. That's why I always, always, always default to using normals wherever possible, unless I'm being lazy. Okay, any other questions about that? So that was kind of a side lesson. We'll move back into what I was talking about here in a second.